He just gave me the thumbs up. So, we're going to get this thing started. As everybody knows, this is being recorded. It will be able to be viewed at a later date for those that maybe aren't there at the Mizzou game. So, I apologize for that, but nothing we could really do. So, I want to start off by saying thank you for everybody that came here right now. And it's very obvious we're all here for the same reason. And what is that? The lake. What happened in the summer of 2025? Next thing is, what are we going to do going forward for 2026 and beyond? I received a lot of questions. Those questions hopefully will be answered during her presentation. So if you sent in a question, pay attention to her presentation on the slides. Your question will probably be answered in a slide. About 30 minutes, she says it should take, roughly. 30 minutes after that, she will go back to the list of questions that I sent her that were not answered on the slide, and she will then read the question, give her comments, and give her answers. This meeting is an hour long. I don't think we'll be done in an hour. The board gave me go ahead to continue on for another 30 minutes if we need to. I would like everybody to, be patient, and please let us know afterwards if you had any questions that didn't get answered. Send the question to the Lake Restoration email, and we'll get you an answer. Might take a little longer than 72 hours, especially if it's a question that I have to consult with Rebecca. So with that being said, I'm going to turn this over to her. She's going to have her meeting the way she likes to run them. We are very fortunate to have Rebecca North here at our lake, so everybody give her a round of applause. If everybody could make sure their phones are on silent so there's no disruptions, that'd be great.
All right, well, thank you, everybody. This is great. I've been involved with this lake. We've been monitoring it since 2020, and then lately, this past year, we've been out to it a few times, and you guys are always very welcome and friendly, and so thank you to everybody for inviting us here. We even had some lake residents as undergraduate students participate in the project, and so yeah, it's been really kind of fun community effort. As mentioned, I'm an associate professor at the School of Natural Resources at the University of Missouri in Columbia. And I study limnology, and so that's the course I teach. I changed the name to lake ecology to make it a little easier for the students who want to sign up and take it. You can also think of it like oceanography, but we're looking at inland waters. So lakes all over the world, and yeah, it's a very ancient science. So you might have already picked up on my accent. I'm Canadian. I moved here about 9 years ago to start my faculty position at the zoo. And so I used to sample lakes like this. So this was about -35 in Saskatchewan in Canada, sampling a reservoir. And so, yeah, done a lot of work on lakes all over the world. I have about 25 years of experience studying lakes and then why they turn green, as yours unfortunately did this summer. I have a global perspective, so as mentioned, most of my history, my PhD and things were obtained in Canada, but I've also worked here now for 9 years, and I did a sabbatical leave in Germany, which is the origins of limnology, so learned lots there, and then this past summer I was in the Netherlands, which was actually really great, and it brought some really great ideas to this lake and this problem, because they have a lot of green lakes. They don't have a lot of water in the Netherlands, and so yeah, they have to come up with kind of creative solutions. And so some of the ideas that I'm going to pitch to you about how we can kind of figure out what to do moving forward have come from these experiences and conversations. So I have over 50 peer-reviewed publications. I brought some of them with me that were relevant to this, so happy to hand out PDF, but these are science publications, so they take a bit to read. My PhD work was looking at iron limitation of phytoplankton, and so I'll start off after this with a bit of a 101 limnology science lecture to kind of try to get everybody on the same place in terms of what we expect to happen when we add nutrients to lakes. So often we're talking about phosphorus and nitrogen as the two primary nutrients, macronutrients we call them, but iron also has a role to play, and so this is some of the work I did on the Laurentian Great Lakes. I've also worked a lot on internal nutrient loading, and so this is often something that's extremely frustrating to lake management because all of the phosphorus and nutrients that you've ever put in the entire watershed around the lake end up in the bottom of the lake. So lake sediments kind of carry that history or that legacy of nutrients from the beginning of the lake. We sometimes look at the processes of releasing those nutrients from the sediments back up into the lake, and that's what we call internal nutrient loading. So I've done some work on that in Canadian systems. And then, of course, most recently here in Canada, it was actually hard to find harmful algal blooms and cyanotoxins to study. And in Missouri, I haven't had any problems with that so far. So harmful algal blooms, refer to these types of phytoplankton that produce toxins. And so you might be familiar with them in the ocean environments. They, red tides, things that are impacting kind of seafood industry produce cyanotoxin. And then in inland waters, it tends to be one particular group of phytoplankton called cyanobacteria. I'll refer to them kind of as HABs or harmful algal blooms or cyanobacterial blooms. And so unfortunately, some of these bacteria, some of the time, have the ability to produce toxins. And it's a very complicated subject, and I'll try to answer your questions and walk you through it. But there's many different types of cyanobacteria. Only some of them have the ability to produce cyanotoxins. Some can produce many cyanotoxins, some produce one, and they don't always do it. So, I would win the Nobel Prize if I could figure out why cyanobacteria produce cyanotoxins. We don't know. And so that's kind of the trick to managing a lot of these things. So it's really hard to come up with that one measurement or one proxy that's going to have you understand what's happening with the cyanotoxins. So more simply put, a lot of my research has been focused on how lakes get from these beautiful blue waters that you want to jump into these green blooming situations. And so there's lots of other case studies in the world. You might have heard of Lake Erie, Lake Okoboji in Florida has been blooming. We're hearing more and more about these blooms more recently. And so I got to know Indian Hills Lake through my role in running the statewide lake assessment program, or SLAP. So instead of MDNR, the Missouri Department of Natural Resources, collecting the water quality data for the state of Missouri, they've contracted out that to the University of Missouri for 50 years. So my predecessor was Jack Jones, and so I was fortunate enough to walk into this data set, and I've been continuing it for the last 9 years. So we sample 65 reservoirs every summer, and have since 1978. And we do it 4 times during the summer, so on a monthly basis. 36 of these, and that's what's shown on the map there, are what we call our primary lakes. And so those lakes have been, sampled religiously every summer 4 times since 1976 in some cases. And so one of those is Henry Seaver Lake. And so some people asked, why I'm comparing Indian Hills Lake in my report to Henry Seaver Lake. And the answer is because we have data for that lake at the same time, so we can look at before and after impacts, but also it's very similar in a lot of ways that I'll go through. So physically and chemically, it is very similar. And all of our data is publicly available. So I have a website, and on that website we have Environmental Data Initiative publications. These are giant CSV files that might be a little difficult to work through, but it is all there. So we publish them on an annual basis, and so that everything up to the 2024 data set is available publicly. So, as Gary alluded to here, I think that most of your questions that you sent in were revolving around, why is the water quality getting worse in your lake, in particular this last summer when you had an extensive bloom. So we can think of cyanobacteria as like, eating or needing to be fed by nutrients, and so we want to starve them, right? So we want to kind of cut off that nutrient supply so they can't grow and bloom. And so the first thing to look at is where are the nutrients coming from and what we can do to prevent them from more of them from coming into the lake. And then, kind of the history of some of the different management actions that have happened to the lake and how we ended up in the state that you were in 2025. But then try to, think positively to the future. We can recover it. Some of you might remember in the 60s, Lake Erie was considered dead, and it's come back to life. It's a little bit of a decline again now. But lakes go through these things, so it's definitely not a dead lake. It will come back, and you can get back to the point where you can swim in the lake for sure. So I'm old. Maybe some of you remember this advertising. This is drugs. This is your brain on drugs. So I tried to stick with that theme. This is your lake, and this is bioengineering in your lake. And so I'm going to refer to kind of these lake management efforts that have happened since about 2020-21 as bioengineering. So we'll talk about some of the cyanotoxin concentrations in Indian Hills, right? So, whether or not you should be concerned to recreate or be around the lake. We'll talk about some of the sources of nutrients from the streams. So again, thank you to all the private lake owner or property owners who have allowed us access to a lot of the streams to the lake, particularly Brush Creek. So we've been monitoring that, trying to figure out if it's coming in from outside of the lake, from the watershed around. Looking at the potential for this internal nutrient loading, so how many nutrients are still in the sediments and will they come back out? Are they all gone? Can we somehow prevent them from coming out? And then I'll try to provide a little bit of interpretation of the previous in-lake management or bioengineering efforts that have happened in the lake. And then, next steps. So, this is your Science 101. So when we think about phytoplankton or algal growth, we kind of think about four main things that can control their growth. And so if you can, pull a switch on one of these four things, you can impact their ability to grow. So one is light. They are photosynthesizers, like trees, like plants. They need light to live. And so they typically only live or can grow in the top of the water column where there's light. At the bottom of the lake, there's not a lot of light. And so most of the things that impact them are happening at the top of the lake. Temperature also impacts them. One of the seminal papers in limnology is blooms like it hot. So we also are kind of, things that we have, very little, in-person control of is the air temperatures, which are directly impacting the water temperatures. And then we have the nutrients, and I think that's the big one to focus on here. So as I mentioned, the two major nutrients we look at are nitrogen and phosphorus. I'm just showing phosphorus here, it usually is the main one. And so, just like we add fertilizer to our crops to make them grow, if those nutrients get into the lakes, they're going to make the phytoplankton grow, just like they do any other plant. And then something I won't talk a lot about, but grazing, we can't forget about that. So what I typically work on, and what light, temperature, nutrients are kind of these bottom-up processes to controlling phytoplankton growth, but of course there's top-down. So, the fish eat the zooplankton, and the zooplankton eat the phytoplankton. So there's other ways that in the past, trophic cascades, we've gone at lake management from a top-down approach as well. And so, lakes turning green is a process that we call eutrophication. And so what typically happens is you get too many nutrients coming into a lake and you get blooms like this. So it's a problem of obviously too much nutrients, too much phytoplankton causing these nasty green colors. But there is some nuances to that you also can get different types of phytoplankton. And so what you want to avoid, and unfortunately what you had in the lake last summer was dominance by one type of phytoplankton, specifically cyanobacteria. And so some of the questions that came in were, can we just remove the cyanobacteria? Can we filter it out? Can we physically get rid of it in some way? The problem is that their average lifespan is like less than a week. And so you can remove them, and in less than a week, if they have the nutrients in the lake, they're just going to grow again. They also have the ability to produce like cysts, and they can live in the sediments of the lake, and they can come back out. People are hatching things out of cores from lakes that goes back centuries. So, they're in the sediments, they're in the lakes, there's no way you're getting rid of the cyanobacteria. So what you need to do is try to manage the lake conditions so that they don't win the competition with the other types of phytoplankton. And so the different types are shown here. So we have cyanobacteria is on the left. Diatoms are usually considered good ones. And these everyone needs nitrogen and phosphorus. But then there's other micronutrients that can differ between different phytoplankton groups. And so diatoms have these glass, frustules we call them, or walls around them, and they build those with silica. And so silica is something that impacts diatom growth, but cyanobacteria have no need, they have nothing to do with silica. And then there's other groups like dinoflagellates, green algae, and other types of phytoplankton that are considered beneficial or good, whereas cyanobacteria definitively fall into the bad type of phytoplankton. So cyanobacteria are not, totally horrible. If everyone takes a deep breath, the oxygen that you're breathing was produced by cyanobacteria. So we've always had them, they've always been here, and as I said, we still have not figured out why they produce these toxins. I'm pretty sure it has nothing to do with humans, right? So it's something that they were doing when we lived in an anoxic environment in which there was a lot of iron. And so they have this high dependency for iron. So if you give them iron, they're going to grow more than the other types of phytoplankton. If you add silica, diatoms are going to grow more than the other types of phytoplankton. So everyone needs nitrogen and phosphorus, but there's some nuances in these micronutrients. So yeah, as we said, cyanobacteria is the oldest organisms on Earth, but they can produce these really toxic compounds. And so mostly I'll talk about microcystin. That's the most common toxin that they produce, and that's the issues with Lake Erie when Toledo, Ohio had to turn off their water supply for about 4 days because they had a bloom come through their intake pipe. That was mostly microcystin. We also, in my lab, measure cylindrospermopsin as well, so it's a different type of toxin, and as I mentioned, some cyanobacteria can produce all 4 of these toxins, some can only produce 1, and some cyanobacteria don't produce toxins at all. Anatoxin and saxitoxin are the other 2 that are measured in my lab, but most of the data that we collected for this lake in the summer was related to high microcystin concentrations. The other tricky part is that there's only regulations for the state of Missouri and from the EPA for microcystin and cylindrospermopsin. So we can't tell you what's too high for anatoxin and saxitoxin because there actually isn't any advisory thresholds for those. So if we want to kind of, tamp down or try to, minimize the cyanobacteria growth, we need to either control the light, control temperature, which is pretty hard in a lake this size, control the nutrients, and so this is nitrogen, phosphorus, but then particularly iron for cyanobacteria, or come at it from a top-down perspective and control them through grazing. So, just again, how lakes function. Typically, most of the nutrients that come into lakes come into through what we call external loading. So a watershed is an area of land around a lake, and anything that drops, like a drop of water falls in that watershed, it's going to eventually make its way into that lake. And so most of the time, things come in through tributaries or streams, and so in the case of Indian Hills, it's Brush Creek, seems to be your major tributary, though it's currently dry. So there's no actual incoming, external nutrient loading from streams happening in the lake right now. But usually we look to kind of, urban or industrial sources of nutrients, wastewater treatment plants, that type of thing is usually what brings nutrients from the external watershed or agricultural sources. And so that could be fertilizer applied to lands, and there's different ways we can try to minimize those getting into streams. But they typically come into the near shore or the shallow areas, and so that's a little bit of a challenge too, right? So we always teach that the solution to pollution is not dilution, but if you have more water, it can handle more nutrients, right? It'll get diluted. And so when it comes into a really shallow area with a smaller volume, you're going to see more of an impact. And then eventually, they make their way into the offshore areas of the lake where they're taken up by the phytoplankton to be able to grow and photosynthesize. But again, the light is kind of always there because we need to remember that those phytoplankton need light. And so they're only going to grow in kind of the surface top areas of lakes. And so we often measure the transparency of the light in the lake with a black and white disc called a Secchi disc. And so there's lakes, like lakes in Africa and stuff, that you can see that disc down 20 meters into the water column. Those are beautiful lakes. This lake, we get a little excited when it gets over a meter. And that's not uncommon for Missouri, right? So, around here, the water quality tends to be in the middle range, and there's a lot of brown kind of color and turbidity. And so then what happens in the summer is as the air temperatures warm up, the lake warms up with them, and we get this difference in temperatures from top to bottom. And so maybe you've felt this when you're swimming and you're like, wow, my feet are significantly colder than the top of my body. That's because you've crossed what we call the thermocline. And so usually these warmer waters, this happens usually around here in April, May. And so the top waters get warmer, the bottom waters kind of maintain that cool temperature. Around here it's usually about 10 degrees Celsius. Yeah, I'm sorry, Canadian scientists, it's elementary. And what this does is it crosses, it's a density differential. And so phytoplankton and dissolved gases and nutrients have a hard time crossing this barrier. And so it separates the lake into 2 pieces. And so we have the top open waters, and these are mixing with the atmosphere, so they're getting oxygen in from the air. This is where the phytoplankton are living because there's enough light for them to be able to live. And so most of the things are happening in these top layers. And then below the thermocline is what we call the hypolimnium, or the bottom waters. And so this is, again, stuck, it's not able to interact with the atmosphere. There's no primary production happening there, so the process of photosynthesis produces oxygen, but it's too dark down there, so that's not happening. And so oxygen is just going to continuously decrease over time throughout the summer. And so as the phytoplankton kind of grow on the surface, they're going to die and sink into the bottom of the lake. This is going to undergo decomposition, and so the green is the photosynthetic cyanobacteria, but there's also heterotrophic bacteria, and that's the purple dots. So these guys typically are most active at the bottom of the lake because they don't need light. And so they're working at the bottom, and they're going to take that organic material, and they're going to decompose it. And the process of decomposition consumes oxygen. So they're using up all the oxygen in the bottom when they're active. And so you can see often these declines over the course of the summer. So we were out sampling the lake just yesterday, and the lake has turned over. So in the fall, we get similar temperatures from top to bottom, and that whole lake mixes and turns over. And this is happens everywhere that there's temperate systems. So all those nutrients that I mentioned that historically have been sitting in those bottom sediments, when that oxygen goes away, it changes the redox conditions at the bottom of the lake. And so phosphorus and iron and things are usually really tightly bound. They can kind of hold on to each other pretty well. But when you take the oxygen away, they let go. And so then you can get this internal phosphorus loading where the nutrients that were stuck in the bottom sediments come back out into the hypolimnium. And then in the fall or the spring, when the lake turns over, it gets mixed up around throughout the whole lake. And so this is what happens with Gulf hypoxia, if you've heard that term. So this is happening in the Gulf of Mexico, and it happens in most lakes as well. And so getting into the management side of things, so the in-lake management processes that have happened over the past couple of years are examples of what we call bio or geoengineering. So this is not new, right? So they used to seed clouds to be able to get it rain on agricultural fields. That's a process where we're using engineering to try to make the biology do what we want it to do. And so this is the timeline I'm sure you're all aware of that happened to the lake. So in April 2022, they added the aerators. So this is the whole lake laminar flow aeration system. And so the intent was to not have the lake stratified like I just explained, right? So to have the whole thing mixed from top to bottom and have oxygen throughout the entire water column. And so this prevented stratification somewhat effectively for the last 3 years. The trick to this whole thing is that two things happened at the same time. So when people are asking, well, was the bloom because of the aerators or was it because of this bio-augmentation program? It's hard to tell because they were implemented within a month of each other. So that's part of the challenge going forward is we don't know which of these two things, or probably it was a combination of the two that caused the bloom. So in May of 2022, this bio-augmentation program was initiated. And so this included adding these micronutrients, including iron. And so I've already just established how iron can get cyanobacteria to grow. And so by adding iron to the lake, you're kind of stimulating that type of phytoplankton. They also added manganese, cobalt, calcium, magnesium, zinc, silica. And so again, silica, I think the intent here was to try to get those diatoms or the good beneficial algae to grow, and because they're the ones that need the silica and not cyanobacteria. Copper, and then they added these enzymes. And so this intent was to kind of, get rid of some of the organic material or muck that's in the bottom of the lake. And so one of the problems here is that bacteria are kind of the same thing, right? So the cyanobacteria that produce toxins that photosynthesize in the top of the lake are going to respond in similar ways to bacteria in the bottom of the lake that they were trying to stimulate to take down the muck. So, by adding these things, you're kind of getting both of those populations because you can't separate them within the lake. And then in July 2024, all of this dosing was stopped for micronutrients and enzymes. And then just this past September, we turned off the aerators. So you won't see the bubbles going anymore in the lake. And so, as I said, we were just out yesterday taking profiles and looking at the lake, and it is now what we would call isothermal. So the lake is the same temperature from top to bottom throughout, and there's lots of oxygen in the bottom waters, which is what typically happens to Missouri lakes every year. And so, yeah, as I mentioned, the aerators are designed to kind of prevent stratification and to bring oxygen to the bottom waters. And so, as I mentioned, we've been sampling these 65 reservoirs every summer in Missouri. And so out of the hundreds of lakes and reservoirs we have in the state, there's only 2 that have oxygen in the bottom waters in the summer. And that's Bull Shoals on the border of Arkansas, where they have like scuba diving because it's so beautiful and clear, and Indian Hills. So it is typical for Missouri reservoirs to stratify in the summer. Every other reservoir in the state has no oxygen in its bottom waters all summer long. And so yes, you can get this internal loading happening, and it also prevents fish from being able to live in the bottom waters, right? Because they like to breathe. And so yeah, the intent was to kind of mix these bottom waters with the top waters and be able to have oxygen throughout the water column. But what also happened is all those nutrients that were in those bottom waters have now been mixed into the top waters, which is where the phytoplankton live and can use it to grow and photosynthesize. So yes, you now have oxygen in the bottom, but now all your nutrients that used to be kind of safely in the bottom and never, where they needed to be at the right time are now mixed up into those top waters with the phytoplankton. And so often when I engage in these things and people say, I want my lake to be better, it's often a question of, well, do you want to have a good fishery or do you want to be able to swim and recreate and drink the water? Because it is hard to have both. Phytoplankton are essential. They're the base of the food web. You've got to have them there to be able to feed the fish. But you're going to come up against this oxygen issue for fisheries. And so just a little kind of example of this. This is what a typical stratified water column would look like in the summer. So we have phytoplankton in the top surface waters, and they're doing their thing in the top, but they're not getting access to that high nutrient supply in the bottom waters because of this stratification or thermocline. If you mix the top waters with the bottom waters, now the phytoplankton are also being mixed throughout the whole water column, so they can go down to the bottom and get the nutrients that they need, and then they can go back up to the top and get the light that they need. And cyanobacteria are like the raccoons of lakes. Like they always win. They can get anything. And so they actually have little bubbles or balloons in them, so they can put lots of air into the bubble. They can float up to the top. They can get the light they need. They can decrease the bubble. They can go back down to the lake and get all the nutrients they need. And they have an advantage over the other phytoplankton in this ability to move around. They're not as much the will of the waves as the other phytoplankton. So I think that's part of it, right? So micronutrients were added to the lake, so you kind of fed the cyanobacteria in some ways, and then by mixing the water column, all of those nutrients that used to be in the bottom waters and not accessible to the cyanobacteria have now been mixed up and are accessible. So that's kind of part of the challenges, and so we can see, I'll show you some data now, that there was increased nutrients in those top waters. And so yeah, just a bit more on iron. So this addition of iron, as I said, I think was intended to stimulate those bottom bacteria, so they eat all the muck, but it also stimulated the cyanobacteria. So cyanobacteria love iron, and the image here is there's actually been a lot of experiments. I think I have a link in my report, where in the oceans, in order to fertilize the oceans, to get them to grow more, to pull down more carbon dioxide, they add iron. So there's lots of history here. When you add iron, you get a lot more cyanobacteria. In terms of silica, as I said, it was intended just for the diatoms, which are good phytoplankton that you want to have there. So cyanobacteria don't care about silica at all. And we know that if silica concentrations are less than this number, 0.19 milligrams per liter, then the addition of it will stimulate their growth. So if your lake had less than 0.19 milligrams per liter of silica, adding the silica would likely have given the diatoms the advantage, and they could have maybe fought against the cyanobacteria a bit more. But my lab did measure the silica in the lake in 2020, and it was 1.6 milligrams per liter. So let's say somebody gave you a burger and you ate it, and you were full and you were happy. And then they gave you 8 more burgers. You don't care, right? You're not gonna do anything with that because you're already full, you've already got what you need. So I think the intent with the silica additions was valid, but there was already so much silica in the lake that it didn't really move the needle on that. So, to take kind of a scientific approach to this, to try to figure out, well, what did these things do? We went with this BACI approach. So before, after, control, impact. And so this kind of allows us to, a lot of the questions we were getting about Indian Hills is, was it a really bad summer? Do we see a lot of other lakes with this happening? Was this an environmental thing? And so in order to kind of assess that, we compared it to Henry Seaver Lake. And so the data I'm going to show you is Indian Hills before. So as I mentioned, the MU Limnology Lab sampled in 2020, and then Restorative Lake Science sampled it in 2021 and 22. So they shared, I'm going to use their data for these comparisons. And that was a question too that I want to address. I wasn't being critical of RLS's methods, I just don't know what they are. So when we measure nutrients, we use instruments. When we filter things, there's different pore size of filters. I just don't have the details on RLS's methods to know if they're apples to apples to what my lab does. So that could be a next step thing. I can reach out. I'm sure she'll share them. I'm sure it's fine. I don't know. Was the only point there. So we looked at Indian Hills and Henry Seaver before treatment. Treatment happened in 2022. So then we compared this with Indian Hills and Henry Seaver Lake after 2022. We have rushed in my lab the analysis of some of the 2025 data, but we typically don't have to report the data until March of the following year, so the Henry Seaver samples have not been analyzed yet. So I don't have 2025 data for Henry Seaver yet. So that only goes to 2024. So Henry Seaver is considered to be a control lake, right? So nothing changed, they didn't add anything. As I mentioned, it's a very similar lake in a lot of ways to Indian Hills. And so, you kind of hypothesize, your guess on this would be that if Henry Seaver water quality was similar to Indian Hills after bioengineering, then it was not due to the bioengineering, right? If they all trended in the same way, then it wasn't something that happened to this lake. And so that's kind of the approach I took to looking at this. So these are the long-term trends on the two lakes. And so on the left, for all the figures, it'll be Indian Hills, and on the right, it'll be Henry Seaver. And so you can see they're very similar physically, so they have similar depths, similar size of watersheds, and then similar what we call trophic status. And so this is similar nutrient concentrations, similar chlorophyll A concentrations, which is a proxy for phytoplankton biomass. And so I looked through all the lakes that we had data on and chose that one because it was the most similar to be able to compare. And so this is a lot of points on this, but the key thing is that there's no trend in either lake for any parameters. So at the year 2020, your water quality actually was not getting worse. It was staying the same. And so was Henry Seaver. And so often we have this perception of things, or people are paying more attention, right, to things with time. But based on the data that we have back to 1976, there was no statistical change in any of our water quality parameters over time for both Indian Hills and Henry Seaver. And so this is just some data to kind of illustrate these examples. And so this is total phosphorus, which is one of these nutrients. So for all these figures, Indian Hills will be on the one side, and then we'll show the before data with that dotted vertical line, and then the after bioengineering treatments, and then Henry Seaver. And so you can see actually you were better. Indian Hills had better water quality than Henry Seaver prior to 2022. And then after, you can see this large jump in phosphorus. This is not a lot of data, but I'll try to speculate a little bit. That could be because, that's when the lake mixed. And so all that bottom nutrients were at the top. And then it declined significantly because the phytoplankton ate it. Or they used it to be able to support their growth. And then it jumped back up again. This is total inorganic nitrogen, and so there's lots of different types of nitrogen. So here I just summed the ones that are most biologically available to the phytoplankton. And so you can see here before, they have these kind of similar concentrations to Henry Seaver, and then after, again, there was a significant increase. And so with internal phosphorus loading, you can also get ammonium release from sediments under those anoxic conditions. So that might be related again to the aerators and the lake mixing, how that jumped up. And so then you can see in Henry Seaver, it was kind of boring. The data didn't have the highs and lows that Indian Hills did. And so it's not just the absolute concentrations of these nutrients, it's the ratio of them, right? So if you're working like a production line, it's the slowest guy on the line that dictates the product that comes out at the end. And so that's kind of the way we can look at the ratio of nitrogen to phosphorus. And so we have these, metrics out there, so we know that if total nitrogen to total phosphorus ratio is less than 20, that means that the lake is limited by nitrogen, which basically means that if you add more nitrogen, you'll get more phytoplankton. And similarly, if it's greater than 20, then it's limited by phosphorus, and so if you add more phosphorus, you'll get more phytoplankton. And so you can really see here how Indian Hills flipped around this. So prior to, it was limited by phosphorus, which is very common for Missouri reservoirs, and then after, it was limited by nitrogen. So I think, in this case, this lake, we're looking at limiting both nitrogen and phosphorus inputs into the lake. Whereas Henry Seaver kind of went the other direction and became more phosphorus limited. So as I mentioned, cyanobacteria tend to win in most battles. One of the other advantages they have is they can literally pull nitrogen from the air. And so when you think about crop rotation systems, right, we often have corn, and then we plant soy in, alternatively, because soybeans can pull nitrogen from the air. And so cyanobacteria are doing that same function in lakes. So they're a bit dangerous in a nitrogen-limiting environment because they're always going to win because they can get their own nitrogen. And so this is an example of a cell of cyanobacteria, and this is the kind of specialized cell that they produce to be able to do this. So when they have a lot of nitrogen, they also can produce nitrogen-rich compounds, right? They have a lot of it, then they can afford to produce things. And unfortunately, microcystin, one of these cyanotoxins, is one of these nitrogen-rich compounds. So, I think that's what's happened, right? The cyanobacteria took over, they outcompeted the other phytoplankton because they're able to get the nitrogen they need, and then they were an abundance of everything, so then they decided, let's produce some toxins. So as I mentioned, we only have criteria for microcystin and selenoxamopsin, and microcystin is pretty much the primary one. So the recommendation limit is 8 micrograms per liter for recreational use. There's drinking water ones, but I hope you're not going and drinking Indian Hills lake water on a regular basis. So 8 is the magic number to kind of compare the next series of concentrations to. So some of the scums had over 3 micrograms per liter. The WHO, the World Health Organization, has a limit of 1. So 3 is higher than 1. But that was in the scums, right? So that wasn't in like the lake proper itself. That was where it was kind of accumulating and piling up along the shore. These are the concentrations from the actual lake itself at the dam site. So right in front of the dam is where we always sample. And so Indian Hills, you can see, really didn't have high toxin concentrations prior to treatment. But after treatment, they've significantly increased. They're still well below 8. So that's why the lake didn't get closed this summer, kind of at your own risk below that 8. Whereas Henry Seaver, over time, has been decreasing in microcystin concentrations, and they're all still pretty low. So, kind of this weight of evidence of looking at things, it does appear that the mechanisms that happened in 2022, the bioaugmentation and the aerators, caused worse water quality in this lake relative to these kind of reference ones. One of the other questions was, is it just the surface scum that we see the cyanobacteria or the toxins? And so this is we have an instrument that measures phycocyanin, which is a pigment. It's representative of cyanobacteria only. And so you can see that, it does kind of blip high at the top, and then as they die, our instrument's picking them up in the bottom of the lake too. So they are kind of throughout the water column, especially when you have the aerators going, right? Because it's mixing everybody from top to bottom. And then typically there's a 2-week window for the cyanotoxin concentration. So they say, wait 2 weeks after you have these really high hits before you do anything in the lake. But some data and experimental stuff actually that I did in Germany and stuff suggests it's a bit longer than that even. So after you have a high toxin concentration or bloom, I'd avoid trying to be in the water for at least 2 weeks, if not more. And the other problem with cyanotoxins is they can enter the food web. And so they're detected in fish tissues. And so they could be in the fish that you're eating from the lake as well. Microcystin is a liver toxin, so it will just accumulates most in the liver and not want to be you eat your fish litter. So, you know, by seeing the fillets and stuff like that, you're probably not getting exposed as much, but there is some documented evidence and that you can get high concentrations of microcystin in your fish as well. So it's not just the water, it's throughout the water column. And so, yeah, just kind of looking at where the nutrients are coming from. So in terms of external nutrient loading, they could be coming in from the streams, was the thought. And so we set up monitoring stations at Brush Creek, Cove 7, and Cove 1. Cove 7 and Cove 1 are dry the majority of the time, and so that was pretty negligible nutrient concentrations. And Brush Creek had similar phosphorus concentrations to the lake. So if it was significantly higher than the lake, then we'd be like, okay, maybe we do have a lot coming in from Brush Creek. So there's some coming in, but it's not going to be the major input. And in fact, it had lower nitrogen than the lake itself too. So the next thing to look at is the lake shoreline, right? So what's happening along the perimeter of the lake. And these are mostly fertilizers. So if you're going to ask questions afterwards, like what can I do today to help with this? Don't fertilize your lawn. Right, so if you add nutrients to your lawn, they're going to end up in the lake, and it's just like you're dumping nitrogen and phosphorus into the lake. So I would advise not to do that. And then the other topic of discussion is whether there's some leaky septic systems. And so there's lots of nitrogen and phosphorus in your waste. One of the ways that you can detect or source waste is looking at E. coli. So E. coli is a fecal coliform that's produced. So it's in your poop, and if it gets in the water, we can detect it. And yesterday I collected some samples from 5 different spots around the lake that will tell us if the E. coli in the lake is from human sources. And so if it comes back that it's all from human sources, that's going to indicate that there's a septic system problem. And so yeah, I just sent them to FedEx yesterday afternoon. We don't have the data back yet, but we'll be sharing that when we get it. And see where some of these nutrients are coming along with the E. coli. And so then the other place to look is the lake itself and into the lake sediments and look at internal phosphorus loading. So one of the things that I don't know the answer to yet is when those aerators were put in and it was all mixed, did you already mix all the nutrients that would have been in the sediments into the lake for the past 3 years? So maybe you did flush the sediments, maybe they're all out of the sediments and that's what caused the bloom. But maybe now there's not a huge nutrient bank in those bottom sediments. Or maybe there is a lot of nutrients in the sediments still, and by capping or doing something to the sediments, we might be able to prevent another bloom next year. So we took one sample when it was stratified. So this is the other thing that's a bit confusing to me is the aerators should have been completely mixing the water column. But when we came in the summer on a few occasions, the lake was still stratified. Especially in front of the dam. So the aerators weren't actually mixing it, and it seems like they were kind of on and off. So we actually just installed the past couple days thermistor chains in the lake. So there's like a cement block with a rope and a boat buoy on top. So if you see those, please leave them in the lake. They're there to record these measurements. And we're now recording temperature in 15-minute increments. So we'll have more ideas, because we were just coming monthly, and so we come 1 month and we're like, yep, the aerators are working, it's the same temperature top to bottom. We come the next month and we're like, oh, no, now the top is warmer than the bottom and it's stratified. So it's hard to say whether or not that has flushed all those nutrients into the lake, or maybe there's still some sitting in the bottom. So the one time we did collect some samples, the bottom waters had the same phosphorus concentration as the top waters, which indicates that it's not still loading into those bottom waters, and maybe we flushed it. But yeah, so that's something that's a bit of an unknown. And so one of the things we're suggesting is to go and measure that. So you can collect a sediment core from the lake. So we can go and get a whole stack of sediment from the lake, bring it into the lab, and measure how much phosphorus is coming off on a daily basis to get a rate. And we can do that under anoxic conditions and under oxic conditions to see whether or not next summer that's going to continue to come out, or whether it already is all come out. So these are our kind of 5 proposed solutions, well, not solutions, things we can try, and things we need more information on before we kind of go ahead and do things. So we want to be cautious. I think we've learned, by just dumping stuff in the lake and then having to figure out what happened after the fact is a little more challenging. And so, I'm recommending we go into this kind of knowing and having predictions about what's going to happen before we just try things and wait and see. So monitoring is part of this, so my lab can continue to come on monthly. We have 4 lake stations set up along the length of the lake that we're collecting data from, and then we'll sample those 3 tributaries when there's water in them flowing into the lake. So we also, as I said, put out these thermistor chains to try to figure out what the mixing dynamics are like. The other thing I'd like to do, and this is an idea I got when I was in the Netherlands with a modeling colleague, is to create a digital twin of the lake. So we currently have enough data to do that based on all this monitoring data. So we can make a computer model of the lake. We can like input what we know about it and then kind of make it work so that it can respond to things. So we can have a model that will work and we'll say, hey, what would happen in the model if we put aerators in? And so we can turn some knobs in the model, we can mix the lake, and then we can figure out what's happening to the phytoplankton. Or we can say, if we didn't have aerators, what would that do to the lake? So that's my kind of maybe more cautious but proposed approach is let's build a model, play with the model instead of playing with the lake, get some informed answers, and then decide what to do next year. And so, as I said, we have the data we need to do this. I just need to hire a modeler because this is not within my skill set. But I do have this collaborator in the Netherlands who has done this before, and so if anybody wants the details, there is some papers here of examples of where they've done this similar thing. They weren't addressing aerators, but it's easy to just turn knobs on a model and get these outputs that can inform us on where the problems are and how to move forward in the future. As I mentioned, we can also do this internal nutrient loading experiment and actually get rates and figure out how much nitrogen and phosphorus is still in the sediments, and then how much could potentially come out if the lake stratified again and we had those anoxic bottom waters. As I mentioned, we did this E. coli sourcing, so we'll come and do it again in the spring because that's more when things run into lakes. But yeah, kind of just looking if the E. coli, and then assuming that nitrogen and phosphorus come into the lake with E. coli, if it's human derived or not, and then we'll have to look at septic systems. And there's easy things to kind of do first with septic systems, right? You can put a dye in your toilet and flush it and see if the lake turns red. There's some little easy things that you could do as a community to just kind of try to figure out if you need to focus in on septics. And then the other thing is planting some vegetation. And so this is what we often suggest in like agricultural settings to keep nutrients on farm fields and not getting into lake and streams is to put like buffers or ditches in place. And so there's lots of plants out there that are really good at taking nitrogen from the soil or the water and undergoing this process called denitrification and blowing it off as gas. And so that would really help if, with Brush Creek or areas of the lake, we're bringing nutrients in. If we put a bunch of plants in front of it, so there's a physical barrier that can cause, sedimentation, less nutrients getting into the lake, but also those plants will be able to get rid of a lot of the nitrogen, specifically in phosphorus a little bit. So let those plants take up the nutrients and let them grow instead of letting the nutrients get into the lake and grow cyanobacteria. Things that work really well are cattails, which I know are not as desirable. But we have been talking to Missouri Wildflowers, and they recommended 3 other ones. So there's irises, there's water willows, and then there's pickerelweed. And those are 3 things that could grow well in like 2 or 3 feet of water and can help to kind of remove the nitrogen. Looking ahead to maybe planting some of those by Brush Creek to just at least minimize the few nutrients that are coming in from there as well. So some people ask some questions about, well, would this help, would that help? And so, to address those, not recommended actions, from my opinion, is the lowering of the lake levels. So as I mentioned, the dilution does kind of help a little bit. And so if you lower the lake levels, then you're going to have less water in the lake, and then those nutrients are going to be more concentrated, and you're going to get more cyanobacteria to grow. So I wouldn't recommend that. Another one was adding dyes. So as we mentioned, they need nutrients and they also need light. And so sometimes you can cut off their light supply, and that could regulate them. But the adding of the dyes, well, your lake would look like a toilet bowl, for starters. We don't really know what impact that would have on the food web or the fisheries. It would likely impact the fish because it's going to, cut out the light for all the phytoplankton, including the good ones. And it actually tends to do better at getting rid of macrophytes, like cattails and these things that I just mentioned are really good to help improve your lake and not as good at cyanobacteria, which is what you want to target. So yeah, I don't think a light limitation or adding dyes would be helpful. And then adding other natural microbes or bacteria. I mean, the lake's got lots of bacteria. It's doing quite well on that, and I don't think you need any additional kind of ones to add. So yeah, that's, I think, yeah, all I had. There's a few questions that as I mentioned by Gary, that I didn't address in my talk, so I can just address those now and then open it up if anybody else has any additional questions. One question, what can we realistically do to keep this from happening again? And so I think I'm proposing more information, more data. We'll spend the winter, nothing's going to happen now. The lake is turned over. It's very uncommon to see blooms in the winter, but we'll continue to monitor it year round and take toxin samples year round, so we'll report back if any are high. But yeah, I think just figuring out what's going on, collecting a lot of data so we can go into the spring with a defined plan. Then the next question was about septic systems. So could that compound the problem? And the answer is yes. Lots of nutrients can come in with septic systems. So, kind of checking your own septic system to make sure it's not leaking might be a good first step. Another question: how often have we had blooms like this in the past? And the answer is never. At least not since 1976. So this is definitely, as I said, something that's happened to this lake. And it looks like it was these bioengineering things, but I can't tell if it was the bioaugmentation or the aerators, and probably a combination of both. So prevention has to come from reducing the sources that are causing the bloom. Is this understanding correct? Yes, we need to kind of deal with the nutrients coming in, and every little bit counts. Yeah, so some said, we see HABs earlier and earlier in the year. So yeah, we do know that lakes are getting warmer earlier, and they're staying warmer longer, as we've just seen. This is a super long summer. It's October, So this is happening everywhere, and so we're also combating. It's getting harder to monitor and look at these cyanobacteria because of the environment changing around us. Another question: do toxin-producing HABs accelerate faster year after year? Not really. It's not like they're running away and we can't stop them. It's kind of a reset button most of the time in the year. There is the sediments, so whatever's in the sediments could continue to come out, but I don't think the lake should be written off. We can definitely get back and recover the situation. So when will we start treating the lake rather than waiting and testing? As I mentioned, we don't know enough, I think, to be able to start treating things. If we get into it and we realize, yeah, it's the sediments, there's a ton in there, then there is things you can add to kind of cap the sediments and prevent them from getting out. That would be, in my opinion, a better thing than like dredging or something, right? Because that's, again, just going to mix everything up and be really messy, and it's quite expensive. I mean, all these treatments are rather expensive, I will say. At the end of the day, what we recommend as ecologists is dealing with the source of the problem instead of trying to fix it with a Band-Aid. And so, if you want to invest in the long-term future of this lake, I think preventing those nutrients from getting in and dealing with the nutrients that are in there is the path forward, as opposed to adding these products and then you might get one good year. The products work in some situations. I've seen it work really well for the Olympics, right? So when you have swimmers that have to swim across a lake and you need that lake to be super clear for a week, sure, dump a bunch of phosphate in, it will lock up the sediments, things will look great, you can have your Olympics event, but that lake's going to bloom again in about a month. And again, these are really expensive things, so continuously dumping them in is going to cost you a lot of money. Will the winter kill the bloom? Do you expect us to safely be able to swim in the water next year? So yeah, the bloom is gone, so it's likely in the bottom of the lake, but as I said, there's still oxygen in the bottom, so it seems like it's okay now. Can't predict what's going to happen next year, right? But we can build a model that we could use to make predictions. We can turn the temperature up in the model and see what happens, right? So we would have more information with that model. Yeah, so if somebody's here, there's some questions that I don't quite understand because I don't know what the acronyms mean. So if the person that asked this is here, please elaborate. So can Mizzou help you push the AHJ, agency having jurisdiction, to pursue corrective action? I don't know.
Well, if we find, that is my question.
Okay, cool.
And clearly the Department of Natural Resources, I believe, is in charge of the water. So if we find out it's agricultural runoff, that's fine, but what are we gonna do about it? Or if it's more human, I think, to your point, gathering more data is important, but it's either gonna be mostly human or mostly animal or runoff. When we know that, what do we do?
Yeah, so this is a private lake. So actually, MDNR, Missouri Department of Natural Resources, doesn't have jurisdiction on this lake.
They would upstream though. If we find out that there's a terrible fertilizer load and you know, you can guess who it's gonna be or make intelligent guesses, can someone help us mitigate them or have them do, you know, mitigation purposes to not pollute the waterway with nitrogen and phosphorus?
Yeah. So the data that we collect through the statewide lake assessment program gets fed into the MDNR to assess nutrient criteria. So the state of Missouri adopted nutrient criteria a couple of years ago, which means that we have criteria that says if your chlorophyllate concentrations exceed a certain number, and we've actually divided the states into different regions, so you're not being compared to the Ozarks or that kind of thing. If it exceeds it, then you're considered to be an impaired water body. And so the chlorophyllate concentrations in Indian Hills lakes do exceed that criteria, so it is considered an impaired water body. This is actually a good thing, because this means now there are mechanisms and funding available to try to fix the problem. And so then the next thing that they're going to do is try to do TMDLs, so total maximum daily loads. So pretty much what we're doing, and we're going to share the data. You know, I'm funded by MDNR, we work closely with them, and so sometimes, like in case of like the Ozarks and Table Rock, we've got models working that they need, and so we just hand them our models and they're using them. So if we build this model, we can also share with MDNR, and they can use it to assess the loads. And so, you know, things that they can do is, once you figure out how much load is coming into the lake, they can stop things, like more so in the public things, but they can say, you can't build another wastewater treatment plant here because the lake can't take the phosphorus load from the output, right? Or you can't have industry here, things like that. So there is actions that they can do through 319 funds, through the EPA, to be able to do it. And so one of the things that I think would be a good first step is, again, this vegetation planting. It's exactly the kind of thing that they like to fund because it's, you know, community, going out and trying to solve a problem. And so that would be a first step. So as opposed to trying to go into private farmers and regulate things, we can at least put a barrier up, you know, between them and the lake to prevent it from getting in.
Does our status as a distressed lake let them be, or would it prompt the Department of Natural Resources to be more supportive?
Yes, but again, because it's a private lake, there's lots of impaired lakes in the state. So they're gonna focus first on the ones that are public and then make their way to the ones private, but I think we can have a conversation with them to help get them to help us out. So yeah, I mean, it's in their best interest to clean up, you know, improve the water quality in all the lakes in Missouri, so we drop below that threshold. And so yeah, so I think there's a conversation to be had and maybe some funding mechanisms to be able to do things. But the things that they like to fund are like, how much phosphorus did you remove from the lake? You know, they want a number, right? So that's why I think maybe the planting would be good, because we're like, put this many plants out, this is how much nitrogen they're removing, this is how much phosphorus, and, you know, be able to kind of show that it's having an impact. I think that might be a good first step.
Thank you.
Yeah, and then the next question was, since grant processes take 9 to 12 months, what steps should the board and the community take this fall and winter to be ready for the bloom? And so yeah, I guess, you know, we apply for funding, but we also do the things at the same time, maybe, right? So, you know, we don't wait for these things to be approved. Things are changing on the federal funding landscape, and so I wouldn't wait to have that, and so maybe we could do both things and then get kind of reimbursed afterwards for having done them. I think, you know, anything that we can come out with data and information, which is what, you know, we're collecting, combined with your, you know, encouragement and interest in trying to maintain the water quality in the lake could be good, would make for a good proposal. And then another question, can the model determine the best timing of turning the aerators back on, and are there better months to using them? So yeah, you only really need the aerators running when the lake is stratified. And so one of the reasons that they're turned off right now is because we're saving a ton of money and energy not running them. The lake, the wind and the cooler air temperatures are mixing the lake naturally. every lake in the state is mixing right now. So there's no need to kind of, help that along by running these aerators. And so I think you're definitely gonna save some energy costs and things by turning them off when the lake is mixed. And so the question is whether or not to turn them back on in, say, April or May, when the lake would naturally stratify again. And so, yeah, I guess, refer back to the model on that one, right? So we can look at the model and say, okay, if we turn them on, what's gonna happen? If we keep them off, what's gonna happen? And then we can come back and report on the model to you in the spring, and then kind of make decisions from there. So that would be my approach, is let's do it online, on a computer, as opposed to actually in the lake itself. And so, yeah, the model we can do anything. We'll determine what depth they should be used. Yeah, so we can also figure out whether or not they're even necessary in the shallower areas of the lake or the coves. Typically, anything less than about 2 meters, 6 feet-ish, would naturally just mix anyways. And so you might not need aerators, they might have been mixing anyways. And so we can figure that out definitely with it. And then, so another question, do we know how much the aerators contributed to the bloom? Because they were done at the same time as that bioaugmentation, there's no way to tell which did it, and it probably is a combination, in my opinion. So one of the reasons that you had aerators was to break up the sludge so it would flow out of the lake. What data is there regarding the muck reduction, and did it actually work? There's always organic material and muck in the bottom of lakes. If you didn't have any, then you wouldn't have a fully functioning microbial system, and it would impact the food web. So no, I don't know. I don't think anyone measured muck loss.
Actually, the measurements were made, bathymetric studies were done prior to the beginning of the whole process, and they published some. I think it's even on ILPOA.org website on how many tons of organic muck was removed.
And did it float out of the lake? That's the part that part I comment.
I don't think it was ever intended to float. It just bioaugmentation, it got consumed.
Yeah, and the lake is deeper now than it was before.
And yes, both anecdotally and bathymetric study proves that it is. So it's kind of good to temper our memory that, SysBio was contracted not to improve the water quality. SysBio was contracted to remove muck, and in fact, the bathymetric studies prove that there is less muck, substantially less muck now than there was before. So I'm not saying that all of it was right. It looks like a lot of it had some unintended side bad consequences, but they kind of did what we asked them to do. They removed muck.
Yeah.
So now we're kind of dealing with things, and we just got to not look to the past and blame, we should have had this, we should have done this. It kind of doesn't matter because they did exactly what they said they were going to do. And now we have a different problem to solve, so let's do that.
Yeah, though I don't think, I agree, I knew bathymetric studies been done, but I imagine the bloom that happened this summer is now muck in the bottom of the lake.
Oh, absolutely.
Right. So you might be back to where, yeah, I don't know.
It had, the muck had built up since 1964,
Right.
so I don't think it all got replaced with this bad algae. Yes, all organic matter will die, especially through the leaves and algae.
So I don't know, we haven't done a new bathymetric study since. What about using plants for filtration is another question. Yeah, great idea. So, one thing you can do is try to keep your shorelines as natural as possible. So, when you pave them over or put things in, then you're not allowing nutrients to kind of percolate and filter, and it's just getting shunted right into the lake. So if you have any kind of vegetation or buffer, then at least that's going to take up those nutrients or physically stop a lot of those sediments from getting into the lake. So yeah, plants are good. Keep your shorelines as natural as possible. Are there other success stories from using the model? And so yeah, for that I'll refer to papers that I'm happy to share and talk about after this. And then finally, can your simulations determine the concentration of nutrients being drawn into the water that will create a problem? And so yeah, we can do things like add a bunch of, like let's say Brush Creek, let's add in 500 micrograms of phosphorus and see what happens, right? So we can do things like that with the model and then run it through and see what it results in terms of sediment bacteria.
As an example, a model in the Netherlands how many variables were being loaded into that to come up with what you can change?
A model is only as good as the data that feeds it. So, yeah, in our case, we are lucky, right? We have pretty good data and pretty good historical data. And the bathymetry work, we've got a good physical understanding of the lake. We've got some chemistry and stuff. So we've got, the phytoplankton samples. I haven't talked about those, but phycotech samples. We've got, which phytoplankton they are over the year. So relative to this, there's worse models out there. So it's a pretty decent amount of data. Always more is better. The internal phosphorus loading work would be nice because we can feed that into a model and say these are the rates coming out in the sediments. And yeah, we have pretty good data.
Can you go over the plants again that you recommended, so we could focus on planting the right things in the water?
Yeah, so cattails do it best.
But yeah.
But if you don't want those, pickerel weed.
Pickerel? Okay.
Yep, and water willow and irises. So they do well in deep water and also are really good at removing nitrogen.
Okay.
This question.
How long would it take to get a model and what would the cost be?
How long would it take to get a model and what's the cost? So I've been told not to talk about costs. So I'll refer back to the board on that one. But basically, yeah, I've got an ad out now to hire a modeler, and if we can't get someone that we want, then my collaborator in the Netherlands has agreed to do it himself. So he's done this before, so it's good to hire right now scientists. So maybe I'll find someone good. And so yeah, if they come with the skills and they know what they're doing, they can do it in a couple months. So we just don't have a point person, but again, we have a backup plan if we can't get that person. So we should be able to get it done by March or so.
You said that the bacteria is gone, but we've got 30 or 40 feet out here on Lakeside Drive. And so, is that indicating a local problem, or is that just wind and current? You can't tell, because it's, if you're seeing it in a certain area most of the time, is that telling us we got an issue somewhere?
It's probably just downwind. Yeah, because they sit on the surface, right? So whatever the prevailing wind is on the lake is just going to blow them, and then they're going to accumulate. So it's more. It could be a source thing too. I have to look at them to see how dead they are, right? Are they actively growing, or are they just kind of piled up and dying?
You said they were gone, so I was just letting you know they're not gone.
Yeah, no, thank you. Yeah, we just sampled the lake, right? So we went in front of the dam, and then kind of the main stations, and then just before the island starts. So yeah, in the main water body is what I should be speaking to.
You touched on it briefly in regards to the fish. One toxin is liver-based, and therefore, if you clean your fish and don't eat the liver, which I'm sure darn few people do, it's not an issue. Some was flesh-based. Does cooking kill it? Are all of our fish safe to eat? I'm trying to get to
Yeah,
the point.
cooking won't kill it. So that's the reason why it's so hard to treat from a water treatment perspective, right? Because it's really hard to get rid of. Like in the case of Toledo, they just turned it off, waited till the bloom to go away. There's no way to actively remove it from things. And it still can be in fish tissue, just in much smaller concentrations than the livers and things. So, if you're interested, we could do a study. I've done this before in Dairy Farm Lake by the zoo, where you collect fish, you dissect them, and then we actually measure the concentrations in their tissues. So it's a thing that could be done, but I'm not aware it's been done here.
Rebecca, I think I can answer a question about the fish. I think it was DNR that came out and they took some fish tissues from several fish. We just haven't got the report back, but they typically are testing for mercury. And I'm sure if the other toxins possibly would be in there, we would hopefully know that as well. So, I cooked some fish yesterday, and a few people did eat some. I didn't tell them where it came from, and they're still alive, so I think
Will your model be able to differentiate the effect of ammonia versus nitrates versus the diatomic nitrogen?
Yeah.
And same thing with the phosphate, the orthophosphate?
Yeah. So the question is, will the model be able to work with the different forms of nutrients? And so I didn't show them all here, but my lab is continuously, since June, we've been measuring ammonium and nitrate and SRP or orthophosphate and total phosphorus and total, all the forms, so that we can look at those, because it's true that there's different uses it's easier to eat some of those nutrients than it is other types of nutrients. So we will have that information, and then, again, data, it's only as good as the model, so we have the data, and so in the model, we can run scenarios to look at what's gonna happen to those forms. A lot of it has to do with oxygen, right? So whether it's nitrate or ammonium has to do with the oxygen in the lake, and so I think that decision is gonna be a lot about whether or not the aerators get turned on or not.
Another question about it. If you find, how often are you doing these dissolved oxygen in the lake? And if you find that that is decreasing in the lake, will that have us turn the aerators on, or how do we counteract that? Because the oxygen locks those nutrients in, right?
Yeah, so we're sampling on a monthly basis, and we're measuring the oxygen profiles, so from top to bottom at those 4 stations. I don't anticipate having issue. If you get ice cover and it stays on for a long time, that can also, cut it off from the atmosphere, and you can get declines in oxygen. I doubt that's going to happen here this winter. So I think the real issues will come up in the spring when the lakes are naturally supposed to stratify. Typically, it happens in like 3 weeks. So as soon as it stratifies, the oxygen's gone. So hopefully our model will be able to inform us before we get to that point to decide about those things. And then again, also with these sediment cores, we'll measure ammonium and phosphorus coming out of them, and so we'll know how much is still down there with the potential to come out if it went anoxic again.
How would you rate the health of our water? Are we stable? Are we in critical condition? Are we on life support? I mean, that was some great information. But I mean, let's get, kind of down to the A, B's, and C's of our health of the water.
Yeah, so it is a relative question. I think I mentioned I'm Canadian. Missouri water quality is a little different than what I grew up swimming in. And so relative to the rest of the state, so we do again have this data from all over the state. Typically, the northern part of the state, the water is pretty eutrophic, what we call, or not great. And then, of course, the best water qualities in kind of the forested regions and the Ozarks, your Table Rocks, Bull Shoals, that type of thing. So 70% of the reservoirs in Missouri are not great water quality. So they're in this eutrophic range. And so relative to the rest of the state, prior to 2022, you were pretty on par. Now, I haven't analyzed all the data from the summer, but we never saw blooms like we saw here in any other lake that we sampled this summer. So prior to 2022, you're fine. This got a little out of control, but as I said, I think we can bring it back. And you are considered impaired, so there is quantitative. Yeah. But so is Lake of the Ozarks.
So we stay on time. Like I said, the extra 30 minutes, we're about there. We'll probably want to take this on maybe a 5-minute quick break before we start the annual meeting. Are there one last questions that we'll take before we close it with Rebecca? I thought she was fantastic. And now that we're going to let her go, she's going to leave with her husband Jake, and they're going to go around to see the Cuba area.